Welcome back, Focus Learners. We've got a really great explainer for you today. We're going to be exploring something that's honestly absolutely fascinating. We're looking at the magical translation process of how computers take those invisible, locked-away ones and zeros and literally transform them right into our physical reality.
Okay, let's dive into this. Think about a computer processor for a second. It's this brilliant brain, right? But it's completely trapped in a world of pure digital data. So an output device acts as the ultimate translator. It bridges that massive digital divide, basically turning pure computation into something that our human eyes, ears, and hands can actually experience and use out here in the real world.
Now here's the foundational theory that really underpins everything we're going to look at today. Output devices basically do one of two distinct things. They either reveal the results of processing in a human-readable format, like on a screen or a piece of paper, or they act as absolutely crucial parts of control systems where the computer actually sends signals to manage a physical process. So definitely keep this concept of the great translator in mind as we go through this.
To make this explainer as efficient as possible for you, here's a quick look at our agenda. 1. Visual output, covering screens and projectors. 2. Tangible output, in both 2D and 3D. 3. Audio and kinetic output. And finally 4. The output decision matrix.
All right, let's jump right into section 1, visual output, screens and projectors.
We're kicking things off with a classic hardware comparison. CRT monitors versus LCD and LED screens. And wow, the trade-offs here are pretty stark. Cathode ray tubes, CRTs, are super heavy. They actually create a physical weight hazard, they run hot, they eat up a ton of power, and they can even cause this flickering effect that leads to pretty severe headaches. Now compare that to modern LCD and LED screens. They use highly efficient backlighting to give you instant maximum brightness, much sharper images, and they are incredibly lightweight with really low power consumption. It's night and day.
So why does this matter in the real world? Well, while LCD and LED are obviously the primary standard today for your computer monitors, tablets, and smartphones, CRTs actually aren't entirely extinct. No way. They still have a very specific niche use in certain CAD, that's computer-aided design, applications. And that's because the older technology actually natively supports the use of highly precise light pens. Pretty cool, right?
Now, I kind of want to challenge your assumptions for a second here. We usually think of touchscreens purely as input devices, right? Like you touch them to make something happen. But take a look at this sequence. First, you provide the touch input, then the processor runs its logic, and then, this is the crucial part, it generates dynamic visual options. So the screen is actually functioning as an output device too, because the visual display actively adapts based on your input. It's a two-way street.
And this interactive feedback loop is literally everywhere. You see it at ATMs, train station ticket collections, museum information kiosks, you name it. The massive pro here is that they are exceptionally space-saving and super user-friendly. The major flaw? Well, aside from getting incredibly smudged and dirty, they are fundamentally terrible if you ever need to type in a long, complex password on them. They're built for simple choices, definitely not for heavy data entry.
Now, what's really interesting about this next one is that projectors solve a very different visual problem. They receive analog or digital signals and magnify the image through a really complex lens system. This perfectly solves that whole crowding around a small monitor problem, which makes it ideal for large training presentations or a home cinema setup. The trade-off, though, is that the hardware is quite expensive, and honestly, the output can easily suffer from fuzziness or low contrast if your room is just too bright.
Moving right along to section 2, tangible output. 2D and 3D.
So when it comes to 2D printing, you really have to match the physical mechanism to the environment you're in. Laser printers, for instance, use dry powder toner and a charged printing drum. Inkjet printers operate completely differently. They spray microscopic ink droplets using thermal heat or piezoelectric vibration. And then you have dot matrix printers. They use physical impact pins to strike an inked ribbon directly against the paper, kind of like an old-school typewriter.
As you can see, matching these mechanisms to their ideal environments is absolutely crucial. Need very fast, high-volume, quiet printing for a standard office? Go laser. What if you need low-volume runs or high-quality single-page photos? Well, inkjet is going to be your best bet for sure. But if you're in a dirty, noisy, damp workshop and you need multi-part carbon copies, that loud, super cheap-to-run dot matrix printer is exactly what you need.
But what if you need flawless, continuous lines instead of an image made up of tiny dots? Well, that is where graph plotters come into play. Unlike standard printers, plotters actually use mechanized pen assemblies moving along the exact X and Y axes to physically draw out vector graphics.
And this mechanical movement is absolutely essential for highly precise architectural blueprints or complex engineering schematics. Basically, situations where scaling up the image simply cannot result in any loss of quality.
Okay, next let's look at the magic of escaping that 2D digital box entirely. 3D printing, or officially additive manufacturing, is a strict sequential process. First up, you create a precise blueprint in CAD software. Second, you use Slicer software to translate that 3D model into exact toolpath routing instructions. And finally, the actual physical build process begins.
So this physical build process manufactures the solid object layer by layer, often using stuff like resin, powdered metal, or specialized plastics. And here's a staggering fact for you. These layers can be incredibly thin. We're talking sometimes just 0.1 millimeters thick. The real-world uses for that level of precision are just unbelievable. We are talking about creating custom prosthetic limbs that are perfectly fitted to a patient, incredibly accurate reconstructive surgery models, and even highly precise aerospace engine parts. It's a real game changer.
Moving on to Section 3, Audio and Kinetic Output.
So, speakers synthesize sound by taking those digital ones and zeros and passing them through a DAC. That's a digital to analog converter, and this creates a continuous analog sound wave. The key advantage here is massive amplification and immersion. But it's not just for making multimedia presentations sound more atmospheric. This is actually a highly critical output for generating synthetic speech via software, which drastically improves accessibility for visually impaired individuals.
And this brilliantly illustrates our second major output definition, which is controlling the physical world. Actuators are these electromechanical devices that simply make things move. Let's look at the solenoid example here. Step 1, a digital computer signal enters the actuator. Step 2, the coil generates a magnetic field. Step 3, that field physically pulls the plunger upwards. And step 4, that mechanical movement opens a valve, allowing fluid to flow. This exact sequence is exactly how digital signals automate heavy-duty motors, pumps, and massive industrial valves.
All right, Section 4, the Output Decision Matrix.
So, how do engineers choose the exact right output device for the job? Before I reveal the final framework here, I want you to step into the shoes of a system designer for just a moment. With all these wildly diverse technologies we've talked about, from glowing screens to physical solenoids, how do engineers logically choose the exact right output device for a specific real-world job?
Well, the secret is that simply memorizing a list of devices just isn't enough. True understanding means knowing exactly when to use them, and that's based entirely on the physical system requirements. This brings us to the Output Decision Matrix. It's essentially a logical flowchart designed to trace your real-world scenario directly to the engineered solution.
Let's move to and see how this builds in practice. Let's say your system requires an output. We start at the top. Do you need tangible, physical output? Yes. Okay, trace that branch down. Do you need vector blueprints? Yes. See how the matrix instantly bypasses all the 3D printers and standard office printers? It leads you exactly to the correct answer, a plotter. It's just a brilliant tool for rapid deduction.
And that really brings us full circle to our foundational theory from the very beginning. Output devices act as the grand translators. They either reveal processing in human-readable formats, or they act as control systems to manage physical processes. Honestly, the whole shebang, everything we've discussed today, from CRT monitors to those heavy-duty solenoids, perfectly fits into this vital definition.
So what does this all mean for you? I want to leave you with this provocative thought to ponder. If you were tasked today with building a fully automated robotic factory from scratch, which combination of these screens, printers, and actuators would you deploy to bridge the digital divide? Think about how they would all connect together. It's like a giant puzzle. Keep analyzing, keep exploring, and I'll see you in the next explainer.